There are two different laboratory techniques that deal with what we've been discussing about of polarity and intermolecular forces. One of them is what's called chromatography. And chromatography is basically the concept of when you put something like ink on a piece of paper. Let's say we put a blue ink on a piece of paper, and then you put that piece of paper into some water. So you've got a beaker that's got some water in it, and you put that piece of paper into it. Okay? Well, what's going to happen, so there's our blue dot. What's going to happen is, and this is biology, what's called capillary action, is the water is going to start climbing up the paper. Okay? Same way that water gets up the roots and into the plant in a plant, during photosynthesis. Okay, is the water will slowly start to go up the paper, and as it does that, the ink will also start to spread out as you go up that paper. So, again, based on intermolecular forces and whether it's polar or not, will determine how much that ink moves. Because if you have different colors of ink, or different inks in general, so let's say 3 different inks, and again, we know that the water in this case is polar. So one of the things you have to ask yourself is the liquid being used polar? Is the pigment being used, the ink, is it polar or is it non-polar? And then what about the chromatography? Okay, let's say you have a non-polar solvent. So let's say this isn't water. Let's say it's something else that's non-polar, like CCl4. Okay, that's a very non-polar compound. Okay, and then the paper is polar. So you've got to think about 3 different things here. You've got to think about the liquid, you have to think about the paper, and you have to think about the ink. Okay, and then which color of ink will move the most? Again, you've got a non-polar solvent and you've got a polar paper. So again, is the ink in this case more attracted to the paper, or is it going to be more attracted to the solvent? Okay, in this case, we know that like dissolves like, and like is attracted to like in terms of intermolecular forces. So since if the ink were non-polar, okay, then it will move more because it's going to be more attracted to this non-polar liquid that's traveling up the paper. Okay, so if again the liquid is non-polar, then the substance that moves the most will be the most non-polar one. Okay, if this is water though, and let's say the paper is non-polar, then which one's going to move the most is the polar one. Okay, so basically if the solvent is polar, if the liquid that's traveling up the paper is polar, then the more polar one will move the most because it's most attracted to the water rather than the paper. Okay, if it's non-polar, then the more non-polar one will move. Okay, so the more polar one moves when the liquid is polar, the more non-polar one moves when the liquid is non-polar. Okay, and then another one is called what's called distillation. Distillation is basically boiling. So let's say you have 2 different things that are mixed together. One has a boiling point around 78, something else has a boiling point around 100. Okay, well what you can do is raise the temperature to about 80 degrees, and what's going to happen is the one that has a boiling point of 78 will boil off, and the one that has 100 will stay. Okay, and that's basically what that paragraph describes, is you use different boiling points of things to separate one mixture from another. All right, now let's get to the important part. So far, everything that we have discussed with intermolecular forces have all dealt with covalent compounds, okay, which means all non-metals. Okay, so what happens when you don't have a covalent compound? What happens when you don't have nitrogen monoxide? Okay, what if you have a metal with a non-metal, or in this case, what if you have an ionic compound? Okay, with ionic compounds, can you use intermolecular forces? No, you cannot. Okay, and that's really what the NO stands for, not nitrogen monoxide. It stands for no. Can you use intermolecular forces? Absolutely no, you cannot, because again, these are molecules. Okay, covalent compounds, we refer to them as molecular compounds many times, which is just another word for molecule. These aren't molecules. These are ionic compounds. They're made up of ions. Okay, so intermolecular forces only refer to molecules or covalently bonded molecules, not ionic compounds. Don't ever use intermolecular forces if they're comparing ionic compounds such as sodium fluoride or magnesium oxide. Okay, when you are talking about ionic compounds, again, no intermolecular forces. What you use is what is called lattice energy. Sometimes I call it lattice enthalpy. Same thing. Lattice energy, lattice enthalpy, same thing. Lattice energy is nothing more than an application of, yes, it's coming back again, Coulomb's law. So the force of attraction between these oppositely charged ions depends on two things. It depends on the charges of the ions and the distance, the bond length, the distance between the two nuclei. Okay, and again, this is only for ionic compounds. So let's look at a couple of examples. The boiling point of magnesium oxide is 3600. NaF is only 1695. Why? Okay, the way you would explain that is that you would say that MgO has the greater boiling point because MgO has the greater lattice energy because the charges are +2 and -2, right? Magnesium has a +2 charge, oxygen has a -2 charge. Whereas on NaF, sodium's +1 and fluorine's -1. The greater charges in MgO create a greater Coulombic attraction. They love those two words together between the ions, resulting in a higher boiling point. That's a great way to kind of summarize it there at the end. Give your reasoning and then talk about the greater Coulombic attraction is fantastic. Okay, and then the boiling point of NaF is 1695, same as before. But that of CSI is only 1280. Why? Again, now the charges are the same. Okay, and this is really, really important. If there is a discrepancy between size and charges, well, this one's smaller, but it has smaller charges. Charges always have the bigger impact. Always. So even if one of them, comparing like AlF3 versus MgF2, well, fluorine's -1, magnesium's +2, aluminum's +3. Okay, that one wins. Okay, I say wins, but that one has the greater lattice energy. AlF3 you would predict to have the higher boiling point. Okay, when the charges are the same though, in this case, NaF does have a greatest lattice energy because, mention the charges first, the charges are the same, they're both +1, -1. But the distance between sodium and fluorine is smaller than the distance between CS and I, which again results in a stronger Coulombic attraction. What do you mean the distance between them is smaller? A sodium atom is smaller than a cesium atom. You should be able to look at a periodic table and see that. Cesium's at the bottom, cesium's in the 6th, its valence electrons are in the 6th shell, sodium's are in the 3rd. Okay, same with fluorine and iodine. Iodine's way down there, fluorine's valence electrons are in the 2nd shell. So that means that the distance between the ions is smaller for sodium and fluorine than it is for cesium and iodine, resulting in a stronger Coulombic attraction. All right, so here's some examples. The ionic radius of two unknown metallic elements, E and M, are shown in the following table. Both elements form oxides, EO and M2O. What does that tell you, though? If E combines with O with a 1-to-1 ratio and oxygen has a -2 charge, that means that E must have a +2 charge. Whereas over here with M2O, oxygen's -2, which means that each M must have a +1 charge. If lattice energy is defined as the energy required to separate an ionic solid and blah, 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 would the lattice energy of M2O be less than, equal to, or greater than the lattice energy of EO? Justify your answer in terms of Coulomb's law. And then they give you the ionic radii, okay? And there were two different ways that you could go about this answer, okay? Because you've got two different things. You've got charges which are different, and then you've also got the radii. They're also pretty different as well. So really, either way would have been accepted. So let's talk about both different ways. Okay, one way you could have answered this and say, first of all, answer the question. It's less than. Because according to the Coulomb's law, the strength of interaction between two ions is directly proportional to the magnitude of the charges. Again, that part you don't need to say. Again, we're just telling the grader, look, I know what Coulomb's law means. Okay, so if you just said E has a charge of +2, M has a charge of +1, therefore the E compound has a greater Coulombic attraction, okay, that would be fine. Okay, the other way you could describe it is also less than, and then you would say, according to Coulomb's law, the strength of interaction between ions is proportional to the distance between them. Okay, and again, there's your mention of Coulomb's law, but again, you could also just say E has a smaller ionic radius than M, so the two ions will be closer together in E than in M, so that will increase, a smaller distance creates a stronger Coulombic attraction, and you're done. Okay? But absolutely, that's one where you could definitely explain that answer in two different ways. You could even mention both of those. You could say, not only does it have the bigger charge, it's also smaller. And both of those things lead to a greater Coulombic attraction, but either one they accepted. Okay, example 4. For a compound, the energy required to separate the ions into a crystal lattice is lattice energy. The following table shows the dissociation reactions and the lattice energy for XCl2 and XBr2. Okay, so we can see here that this one is slightly higher than the bottom one. Okay, and again, in terms of charges, we've got +2, +2, -1, -1. So if it's not charges, then it has to be distance. Okay, and looking at the periodic table, we can see that chlorine is a smaller atom than bromine is, so the chloride ion is going to be slightly smaller than the bromine ion. Okay, so how would you explain that? You would say, explain in terms of atomic properties in Coulomb's law why the lattice energy is greater than XBr2. So I would say because the Cl minus ion is smaller than Br minus due to Cl minus having one less electron shell than Br minus, and the smaller the ion, the stronger the Coulombic attraction, resulting in a greater lattice energy. Okay, and again, what are the key things that they're looking for? Talking about it smaller, and then talking about the stronger Coulombic attraction. That's really what they're going to be looking for in that answer.